Here's another example of graphing using calculus. Let's graph the function f of x equals x over x squared minus 4, pretending that I'm not sitting in front of a computer until the end. So I always like to start with symmetry, although there's other places to start pulling things out of your toolbox. Here, let's see. There's a lot of kinds of symmetry out there, but the ones we usually check for are even, odd, or periodic. It's not periodic because there's no sines and cosines. So we check even and odd by always doing the same thing. We just look at what happens with minus x, and we compare it to what happens with x itself. Okay. Let's see if I can do this. Okay. So the minus squares away on the bottom, but it's left on the top, and so guess what? I get exactly minus of what I started with. So that's equal to minus f of x, and we've found a symmetry. It's an odd function. That means it's symmetric around the origin symmetry. Alrighty, symmetric around the origin, and so that means we can just do the right hand half if we want, and then flip the whole thing, or we could do the whole thing all at once and then use this as a check for our answer that it should come out to be have an origin symmetry. Okay, let's look at the domain. That's something the book starts with. I don't know why it doesn't like a capital D. Okay, the domain of this thing. Well, there are some numbers that can't go in here. X squared had better not be 4. In other words, x had better not be plus or minus 2 to be in the domain. Now, one reason I don't start with the domain is it almost always comes out thinking about more sophisticated things, which is what happens near x equals plus or minus 2. It's one thing to say, oh, I'm not going to graph it there. But usually near a domain dropout, there's going to be something interesting happening. And that's where I like to look at the infinities. Does it have vertical or horizontal asymptotes? And what happens if I look at the end behavior? If it's not an asymptote, we want to look at that. Well, vertical asymptotes, that's going to be something that has any kind of infinite limit. Well, with a rational function, even before we learned calculus, we learned about how vertical asymptotes can come up. It's when this denominator is equal to 0. So we're going to get vertical asymptotes at, guess what, x is plus or minus 2. That's why those domain dropouts are really happening, is because they're vertical asymptotes. Now, vertical asymptotes come in various different flavors in terms of do they go up on both sides, or down on both sides, or up and down, and we're going to have to figure that out. So we could look more carefully at limits. We could do things like the limit as x approaches minus 2 from the left of f of x, for example. We know how to do that, and it's certainly a doable thing, but very often we're going to get that from another tool. We're going to want to look at increase and decrease of this function anyway, and that's probably going to tell us that anyway. So let's skip that in the interest of being efficient. But if you want to do it and you don't think you're going to get the information elsewhere, it's a very good tool to use. What about horizontal asymptotes? Or more general, just because I mentioned the idea of a horizontal asymptote doesn't mean it has to have one. But we want to check it. And the way to check it, whether or not it has one or not, we just take the limit as x goes to infinity. And plus or minus infinity, but let's start with x goes to infinity. And it's a rational function, so that means we can use the cover-up method. So the 4 goes away. It's the same thing as the limit of 1 over x. And that's pretty simple. That's going to be 0. And let's see, you know what? We can do our usual little thing very often. Put a plus or minus in. They're both going to be 0. And again, because it's an odd symmetry, anything going to 0 on the far left, if you flip that through the origin or equivalently rotate it 180 degrees, it's going to be going to 0 on the far right as well. That's why that symmetry is happening. Okay, so it does have a horizontal asymptote. It is 0, the axis, the x-axis. Speaking of the x-axis and the y-axis, we could look at intercepts. And so the y-intercept, that's just f of 0. That's equal to 0. It's good to know. And what about x-intercepts? Well, that's going to be, we're going to set the function equal to 0, the output equal to 0. But you know, the thing about a fraction being equal to 0, the only way that happens is if the numerator is equal to 0. And the denominator can't be 0 at the same time. Well, That's just going to give us x equals 0. Okay. So, I don't know, that's a little disappointing, I think. We've already found the y-intercept. It was the origin. And guess what? That's the only x-intercept as well. The only place it crosses the axes at all is right when it crosses the origin. Okay, so now it's time to take derivatives. Increase, decrease. Oh, wait, sorry. When we've got the intercept information, we often want to look at the signs. And I think I forgot to do this in the other example. It's really, if it's easy, again, all these tools are usually, you want to do them until you get stuck. Let's look at the signs for this function. That's going to be really interesting. And let me show you how a good way to do that. Whenever you're asking both for zeros and for signs, you want to factor as much as possible. This is f of x. Okay. And so let's see what happens. If x is less than 2, then what's going to happen with that? F of x equals, and I'm just going to symbolically put, okay, that's, less than minus 2. I'm going to start at minus 2, because we know interesting things happen at plus or minus 2 and at 0. Those are the interesting x values we've found so far. F of x, if x is less than minus 2, x is going to be a negative number, and a negative number minus 2 is certainly negative. And a number that's less than minus 2, even if you add 2 to it, it's still negative. Hey, negative over negative times negative is going to be negative. Okay, so it's going to be below the axis. Okay, x is, if minus 2 is less than x is less than 0, then f of x is going to be, well, what has changed here? X is still negative. Negative minus negative is still negative, so that's all still the same. There's only one thing that's flipped, and that's positive. And so that's going to be positive. I guess I don't really need it. Well, I'll emphasize that it's a symbolic thing here. Okay, so it's flipped to positive. And notice what happened is it didn't flip from minus to positive by going through a 0. This is the only 0. X equals 0 is the only 0 in this function. It has flipped by going through an asymptote. Ha. Okay. And then 0 less than x less than 2. Now notice we actually know exactly what the answer should be because of the symmetry. This should be the flipped version of this guy, should end up being negative, and let's check that. Now x is positive, but x minus 2 is still negative because x is less than 2, and then that's positive, and surprise, surprise, that's negative. And just to complete it, if x is greater than 2, then f of x is, it's all positive now. Positive times positive equals positive. Okay, so these are the different signs, the different parts of the whether it's below or above the x-axis. It starts out below, goes by an asymptote to above, goes through goes through 0, because that's the one place where it crossed the axis at the origin, to negative, and then goes across an asymptote to plus. By the way, that answers the question I mentioned. We could have done these limit calculations, but basically the way we would have done those limit calculations is exactly doing this kind of sign chart anyway. There's a lot of redundancy. If you do every step in every possible ramification, you're going to have a lot of redundancy. And part of the trick here is to do it somewhat more efficiently. Okay, so that's good to know. Notice here, I'm doing a sign chart on the actual function. I haven't taken a derivative here. We're going to want to do that on the derivative as well, but here I was just doing it on the actual function itself. Okay, now increase, decrease, max, min, critical points, all that good stuff about the first derivative. Alrighty. So f prime of x, we got to actually calculate that derivative. Okay, it's quotient rule. X over x squared minus 4. We're going to get 1 times x squared minus 4, derivative of the top times the bottom left alone, minus the top left alone times the derivative of the bottom, all over the bottom squared. And always, always simplify. X squared minus 2x squared is going to be minus x squared minus 4 over x squared minus 4. Now don't try to cancel something here that doesn't cancel. Nothing cancels here. I am going to take that minus out though, because that's going to be, I think, a little bit easier to understand. Okay, so there's our first derivative. Let's go ahead and set it equal to 0. And but let's notice something. That's interesting. x squared plus 4, that's a square plus 4. That's never equal to 0. And the bottom can't make a fraction equal to 0. And we've already dealt with what happens at the bottom. Yes, there are DNEs here, so let's just make sure we know that. The first derivative does not exist. Let me pause this thing. Okay, back. We know that the first derivative doesn't exist at x equals plus or minus 2, but that's not hardly a shock. There's vertical asymptotes there. So that's not new information. And it's equal to 0? Never. So this guy never has any never has any critical points, because the DNEs aren't really critical points, because these aren't points on the graph. Oops. That's a tricky thing. They're not critical points because there's nowhere on the graph to point to. They're vertical asymptotes. They're points that aren't even in the domain. Okay. And okay, so this guy never actually goes flat. Now, here's the tricky thing though. That doesn't mean it can't change from negative to positive. Just like the function value itself changed at asymptotes, this guy can change at asymptotes as well. Okay, so it might have some increase and decrease behavior. Okay, so let's just go on though. I don't want to make this super long. Let's put that in display mode. Okay, f double prime. Okay, so we're going to take the derivative of this guy. So there's a minus out in front. We're going to get a 2x times x squared minus 4 quantity squared all left alone, minus the top left alone, times 2 times x squared minus 4 times 2x, all over x squared minus 4 to the 4th. Now, always, 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 with the second derivative of a quotient rule, you're going to have a cancellation. 1 power of x squared minus 4 is going to cancel top and bottom. There's still a minus in front. This is 2x, x squared minus 4, minus the x squared minus 4 completely goes away here, and you get 4x times x squared plus 4. And then it's all over x squared minus 4 cubed. Okay. Now what are we getting? 2x cubed minus 4x cubed. So minus 2x cubed. And then a minus 8x minus 16x. Okay. And I can use that minus sign to cancel some stuff. And let me actually go ahead and factor it out. That's 2x times x squared minus 12 all over x minus 2, x minus 2 cubed, x plus 2 cubed. And in fact, let's go ahead and factor this out even. Oh, that's a plus 12. Thank goodness I caught that early. When I used the minus to kill both minus signs, I forgot to kill both minus signs. That's going to be really important, that's a plus. Okay, so how does this let us analyze things? Well, let's set it equal to 0 to figure out possible inflection points. That's going to be at x equals 0, because that guy, and then nothing else. X squared plus 12 can't equal 0. The bottom can't make it equal to 0, and yes, it makes it not exist a few times, which are important points to note, but same exact thing. They're not critical, these plus or minus 2, they're not critical points or inflection points, because they're not points on the actual graph where the concavity changes. It probably is a point where the concavity changes, and we have to pay attention to that, but they're not. It's not actually a place where it can point to on the graph, because it's not in the domain of the graph. So let's go back up and let's extend this table we had. Oh, you know what? I should have made this into a table. Let's make it into a table right now. So let's insert a table. Okay, so x here, and then let's insert some columns. Okay, so f of x, f prime of x. This is a little bit different from a table you might see in the book, that I'm actually going to include the sign for f of x as well, because we already know it, and it's definitely interesting. So x less than minus 2, x equals minus 2, minus 2 less than x less than 2. Oh, let me make that math mode so it all looks the same. Less than 0, sorry. X equals 0. 0 less than x less than 2 in math mode. And x equals 2 and x greater than 2. Okay. Seems like that's all the points we found. We found 0 and plus or minus 2 repeatedly. We haven't found a lot of other interesting points on this graph. Okay, when x was less than minus 2, let's remind ourselves, that went minus plus minus plus. So let me just fill that in. This is information we had already. Minus, plus, minus, plus, and here it was changing because it was a 0, and here it was a DNE. And in fact, all the derivatives are DNEs there. Okay. F prime, we can now, let's see, we know that there were no zeros for the F prime. Now we just have to figure out the signs for that guy. Let's go back up to F prime here. F prime had a positive number on top, it has an overall negative, and then it has a square on the bottom. This guy is always a negative number except a couple times when it doesn't exist. That's really nice to know. That is always, always negative. This guy's always a decreasing function. Oh, math mode. Okay, that was easy. F double prime, let's see. X squared plus 12, always positive. Can just basically ignore it. X, that's going to change at x equals 0, so we're going to have to pay attention to that. And then these guys are going to change as well. Okay, so let's think about the same analysis. I don't know if I'm going to write it out explicitly as we did for the function itself, like when we did this kind of stuff. I think I'm going to do it just audio, and you can fill in the details. It'll be quicker. Okay, so when x is less than minus 2, then this is, guys, these are both going to be negative. They're cubed, but then they multiply by each other, and we're going to get a plus. Minus times minus is plus. Then when x is between minus 2 and 0, and then I forgot the negative up here. I'm rushing here. Minus times minus, no, this is actually going to be minus. There we go. There we go. Negative, negative, negative. When x has crossed between minus 2 and 0, this guy's still negative, cube is still negative. This guy's still negative, but this has turned positive, positive cube is positive. Now it's minus over minus is plus. At x equals 0, that's a 0 for the second derivative. We found that already. And then on the other side of 0, positive, x is positive here. This guy's certainly positive. This guy's still negative, and so we have one negative, and that's going to make a negative overall. And then at the end, x greater than 2, every single thing in the expression is positive. Now let's think about odd symmetry here. I didn't really exploit the symmetry, but let's think about it. Again, the odd symmetry means that this minus should be opposite to this plus. This plus should be opposite to this minus. Well, why aren't these opposite to each other? Well, the first derivative of an odd function, if we look at how derivatives work, it's going to be even. Like the derivative of x cubed is 3x squared. The derivative of sine is cosine. And that actually makes sense. If you actually draw something going up and to the right, and then you rotate it 180 degrees, it's still going to go up and to the right. It doesn't actually flip. And so the first derivative actually should be even function, and that's what we're seeing. You take another derivative, it should be back to that odd pattern. And you notice that the second derivative and the 0th derivative, the function itself, are all exactly the same sign pattern. Okay, so what do we plot out of all this? How do we actually put pen to paper? Well, there's not much to plot. There's one point, x equals 0, where the function is 0, it's going through the origin, and we know it's an inflection point. That's the only point that we've been told to plot here in our list of interesting information. But believe it or not, that's all we have to do. We just start from there and follow the directions. Now here's where I'm going to cheat, and I'm going to actually let it plot the whole thing here. So I'm going to take it down, I'll copy it down here. Okay, and then I'm just going to, well, actually this is a pretty good window probably. Yeah, that's good enough. So suppose we just started at this point here. Let me make it a little smaller. No, not minus 2. That would confuse the heck out of it. Okay. So, well, I don't know if I can get these together. The sign chart together. Well, let me reduce the magnification. Okay, hopefully you can still see that. So you start at the origin, and remember, we only have to do the right-hand side, and then we can rotate it around. So let's just go ahead and start at the origin, do the right-hand side. You start at the origin. That's this point, this 0, 0 point. And then what's the instructions? Go downward until you get to an asymptote. Well, that's going to be the kind of asymptote that goes off to minus infinity. Okay, now flip yourself, and let's see. At the other side of that asymptote, the function has become positive, but it's still decreasing, and it should be concave up. And we know it's supposed to be going towards a horizontal asymptote of 0. You don't see that too much because I don't take it out very far in the x direction, or the computer didn't take it out. But it just keeps going down, 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 down like this. And that's it. Now, in the other direction, it's going to be rotated. So just take this guy and rotate it up and to the left on the quadrant 2. Take this guy and rotate it around. Or alternatively, if you don't want to just use the symmetry, you just kind of carefully go do this backwards. I'm going to start at 0 and then follow the trace of a decreasing function towards an asymptote. If I'm tracing a decreasing function backwards from right to left, that's going to go up towards that asymptote. Then I reset. X minus 2 is negative. It should be a decreasing function still. In other words, I'm going to go up as I go backwards, and it's going to go towards that asymptote x equals 0. Okay. The second derivative, I hardly had to use that information here because it kind of came automatically from all the other stuff, but you can use it as a good check. It's concave down, that's this guy, concave up then down, that's this plus 0 minus, and then concave up, and that's the plus. So that's a way to be really, really sure that this is the right kind of graph of this function.